previous work around 5 or 6 years work. So from a title, you can see that I will share about machine learning and AI-based alloy design. Specifically, there are two parts for myself. For my understanding that I work, one part is on the small data and the small model, which is mostly we focus on the Bayesian optimization on the material design. And another part, the big data large model, is because in recent years, the AI and the deep learning and also the large language models are very powerful, and we try to involve these most advanced techniques in our uh, uh, research. Uh, a brief introduction as a home being introduced that uh, from 2017 to 2020, 24, I work in the Max Planck Institute for Iron Research for my PhD and postdoc, and I work as 1 year project group leader. And then from 2024, I joined Shanghai Jiaotong University as a associate professor, and I have been here for around 1.5 years. Generally, I focus on four parts with AI and materials design, material science. The first part is advanced material design. That is uh, most of my work. Uh, and also, this is also the most popular direction. And when we talk about AI and materials, which means that we use machine learning or AI methods to accelerate the design of the materials. It's easy to understand, right? And the second part is about text data mining. This I need a point. For this part, generally we will involve some natural language processing methods like the large language model, as you know, is very popular now. And another part that I'm quite interested in is that using the the AI to deal with to analyze the experiment data because as you know that for material science we produce all kinds of images from XRD, from 1D to 2D to 3D, from the XRD results to SEM, TEM, and atom probe tomography data. We use these things. I have been working on this because when I was in my postdoc, I work with Baptiste Gaut, who was a group leader in Max Planck Institute, and we did a lot of atom probe tomography, and we tried to use the uh, convolutional neural network to work on the IAPT data. So that's this part. And the last part is explainable artificial intelligence. For me, I think this is the most interesting but most difficult part for AI and material science because mostly uh, the current AI is black box because it's very deep. So uh, the explainable part is very weak, and if we want to get some interpretability from this AI, it's very difficult. It's because mostly we take use of AI to deal with the material science problem. So if the technique this AI uh, is black box, so it's also difficult for us to get some explainable things, right? But now, I try to involve some things. For example, recently we work on this symbolic regression. We think it can be one of the interesting direction, and also we work on some causal inference to involve the causal inference into the explainable part of the AI study. So this generally I'm interested in these four parts. So I share with you with this around 40 minutes or uh, uh, around two parts. One is called small data, small model, and another is called the big data and the large model. Interestingly, that when I talk about the small data, small model part, it actually has little relationship with current deep learning. Actually, it's a pure Bayesian optimization problem with some uh, we involve some generative model, but actually it's not the core. It's not the most important part. The most important part is the Bayesian optimization for this, and also I feel this Bayesian BO is very useful for the small data problem and for the current because in the current material problems, normally we have a small experimental data, and for some also for some industry problems, we also have this situation. So the BO is very useful to deal with this. This is the background that I won't talk too much because there is show that various application of AI. So you are familiar with this, and this is this is one part I want to talk more because we show that uh, the development of the AI methods for the material learn from the original trial and error to the theory guided to the computational methods like DFT and so many methods, and to the fourth generation, we think it's the material informatics. Actually, this is from Obama, and also in China, we started this around 2000 and around 2000, and we did a lot of the high support computation and high support experimentation, and we also use machine learning. Sometimes people said the fourth generation and the fifth generation they are the same because they are data driven, or they can also call the material informatics. But personally, I would like to separate it into two generations because I personally I think the fourth generation informatics, material informatics, or the material genomic engineering is more focused on the data production from experiments or from computation, and then we use some uh, uh, machine learning to deal with the data. I think it's more focused on the data part. However, for the fifth generations, I think it's more uh, focused on the methods, focus on the algorithm or the AI part, because from the 2012, from the Alex Late, which beat the previous support vector machine in the image-led computation, and from that on, the deep learning, the generative AI, and the large language model become so powerful that it's totally different from the previous traditional machine learning. So I think this fourth part, the fifth part, although they are both data driven, but they are different. This shows that the when we deal with some experimental data problems, we have the a very small data set, and also it's more complicated than the image processing problem. Because for image processing, you have a pixel, zero, one, or numbers. It's not so difficult, but for the material things like the high entropy noise, you need to deal with the composition in the phases, lattice, memories, and it's more complicated. And also the current alloy design uh, is try to involve more elements in the alloys. Not only the high entropy alloys I show here, but actually, for example, the super alloys, sometimes they have more than 10 elements in one alloy. Although some of them are very minor, like only a few of the elements, but the composition space is infinite. And also the quantitative theoretic prediction will be more and difficult. So that's the reason that why we use the machine learning ways to data driven ways to deal with the problems. Uh, it has been from now, I think more than 3 years or 4 years since that we published in Science about this work using the AI active learning loop to do this alloy design. Specifically, we focus on the Ava alloys. I think in that time around 4 years ago, it's this work is novel, but now I feel this framework, active learning framework, is quite common in the material design or alloy design. in alloy design, I think. Um, generally, we have four parts in the active learning loop. The first part is that we collect a data set. It's very small. It's around 700 noise. Uh, it's totally different from nowadays deep learning or the large language model that train 100 billion of the parameters. And the second part we involve the generative model. Here we use autoencoder. Now the generative model is also uh, commonly used in nowadays material design. As we know that 2 years ago, Google also published some paper in Nature or Science about the genome. That in that part they use the diffusion models. But here we use the autoencoder. But I think autoencoder, GAN, generative adversarial neural network, and the diffusion models they are over very powerful ways to uh, for the alloy design. Um, here the third part is the ensemble model. Uh, with the neural network combined with the neural network and the boosting tree. So actually, this part, the only thing that we do in this part is that we want to get the mean and the variance of the prediction. So we know that the most part of the Bayesian optimization, or we call the active learning, I think they are generally very almost the active learning or Bayesian optimization because we do many loops, so then we call it active learning, but in principle, it's the Bayesian optimization. The most important part of the Bayesian optimization is the exploitation, exploration, and also you can call it the utility function. And for that, you need to get the mean and the variance of the prediction. So we do the ensemble regression. The most part is that we want to get the mean and the variance. Also, we involved this DFT and the thermodynamics calculations to increase the performance of our model. Here I want to mention one very important thing that I want to go back to the this page. So why I want to go back to this page because I want to state one thing that sometimes people think that the new generation of the material design will replace the old generation of the uh, material design, but that's wrong. So the thing is that this the big advantage of this new generation of the AI is that it can involve all the old generations into the one generation into the AI to accelerate the already. For example, this computational methods, the calculation actually can be involved into this AI part, and also the trial and error, the data can also be involved, and also the high throughput and experimentation results can also be involved. So this fifth generation is that it not replace any of the previous generation. It's a integration of all the previous methods. And then it can be very powerful because it integrates all the methods and all the data. So that's why that's the advantage. So here we involved this DFT and thermodynamics calculations because sometimes we found that the calculations maybe not so accurate with every number, but sometimes the trend is good. So this can also improve the performance of the machine learning model. The last part is the utility function, and you can also call it accreditation function. It's the same, and we use exploitation and exploration to accelerate this design and choose some alloys for experimentation, and then get results back to the dataset and do the active learning loops, and again and again. About the exploitation exploration part, I will introduce later. And the first part is the generative model. This is some mathematics things I will not talk too much. Actually, with the most important thing is that we get latent space is like this, and there's some clustering of the different alloy system, and then we get this ensemble regression models for these two parts. We get you may ask that why we do the two stages of the regression models. Actually, these two stages are exactly the same. Its only difference is that for the first stage, we have more than 1,000 candidates that we do a rough selection of the compositions. And then in the second stage, we add some DFT and thermodynamics, and then we have some 10 to 30 high ranking lawyers. This is because the DFT calculation and some they are time consuming and expensive. We cannot do in the first stage because it's too much. We don't have so many computation sources to do this. So that's the only reason that why we do these two stages. Actually, they are the same. And also, I said that the only thing we want to uh, get is the mean and the variance for the prediction. Um, Actually, to be honest, when we did this in 3 years ago, actually we are not so clear about this details. For example, here we use 50 neural network and 50 boosting trace. If you ask me why we use the 50 plus 50, actually, I have no idea about that. I think we can use 100 plus 100, and maybe it doesn't affect too much. And also you can use 10 plus 10, and also you use Gaussian GPR to here to get the uncertainty here, or use the Bayesian neural network to get the uncertainty here. I'm not if you ask me, I'm not sure about that, because we didn't think too much, to be honest, at that time. Uh, um, the only thing that we want to get the uncertainty, and then we got the uncertainty from this. So this is the as I said, this is the core of the uh, active learning or Bayesian organization is exploitation and exploration. That's a very efficient way to deal with the uh, small data set, for example, in the alloy data. So what is exploration and exploitation? Actually, it's easy to understand. The exploitation is that with the model, you want to design the alloys which has a good performance you want. For example, the high strength or low thermal expansion coefficient. Here we want. So it's very strict. So you want what you want. You want the alloy with good performance. You choose the highest, the alloy with highest strength and to do it's easy to understand the exploitation. But the problem is what is exploration? Then this is connected with another concept called the information entropy. So, which means what is information entropy? Is that you give me some information that I uh, get more knowledge. For example, if you told me that tomorrow the sun will rise, so it's nothing for me because I think the sun always rise tomorrow. But you told me that tomorrow it will be raining, so that will be useful. It has a higher information entropy. I also sometimes give another uh, example is that Trump, his words has a very high information entropy because he is unpredictable. You don't know what he will say. And so sometimes, so what is the use? What is the use of the information entropy of these results? Sometimes if you want to improve your model's performance and you want to explore the unknown regions, you need the data with more information entropy. That will give the if you give this data back to the model will get higher uh, performance quickly. So you can see this is two-part exploitation. You want to get the good materials quickly, and the exploration that you want your model to improve the performance quickly. So this is not the same things. And so that's why we have the utility function. It's an explanation of the exploitation and explore. It's a combination of exploitation and exploration. For exploitation, we more focus on the predicted mean. Then we can get the good results. Exploration that we more focus on uncertainty which will give us more information, give more things to the model. So that's why we choose the utility function to combine the exploitation and exploration. So here we choose the top three alloys for experiments, and then we get the results. So the results part is also very interesting. So first, let's focus on this part. So this part we want to see that in the ideal situation, we always have only one local optimal or local minimum. But in real situation, that we have one more local minimum. So that's why we always need to do exploration. That's the reason. And how why and what's the reason that we have this real situation is that actually the reason is from the data set. When you have a small data set and also the distribution of the this has a big bias. So it will, for example, here we give the example of the chromium and the copper. You can see that most elements have no copper and some of them only have 5% of copper. Many places are unknown and the distribution are very biased. So that's why we have more place to exploration, and also we need we have more local optimal to explore. And this part shows the results. This is the most important part for this work. The left part, this is the predictive results, and the the right part, experimental results. So the most important thing is here, the most important thing for this part is the randomness. What is randomness? Which means that uh, the prediction can be very different from the experimental results. And sometimes we get good results at the beginning, but we didn't get uh, better than the first one, but we also get a better one. So what I want to see is here that when you have a small data and a very big bias data, you always have a randomness for the results. Uh, if I, for example, if I do this thing again, do another 6 iterations, the plot can be totally different. And I have no idea which iteration I can get the best results. So the best can be happens in the third or fourth. I have no idea about that. And when we submit this paper, reviewer also discuss with us or judge our work, because they think it's he think these results should be more steady. But actually, we told him that if you have a state data, you cannot avoid this randomness. We cannot lie. We can have a very clear results that uh, very beautiful results, but actually it's not the truth. The truth is that you have a small data to do these things. You cannot avoid this randomness. Sometimes you have some parts you can control, but you have a lot of part you cannot control. But then your question is that if it has so much randomness, how can you prove that this machine learning based, this active learning based work is useful? Then we prove that from statistic ways. If you if you check every single point, it can be right. It can have much randomness, but if you check the whole trend, you can see that our model are learning, the total error are decreasing. So that's our results. And also then we found some alloys with no thermal expansion coefficient, and that's our results. And then we recently we also did some recent, late uh, seminar work like uh, a few days ago we just published this work on pillars with the basic info for the hydrolysis with the uh, 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 mechanical property improvement. So the thing is that for mechanical properties, the process and the microstructure has more effect on this. For the thermal expansion coefficient, it's more intrinsic things. So that's a difference. Actually, it's more difficult. If you want to involve the process and the microstructure, it's more important, more difficult than only consider the intrinsic property. And also we did some following on superalloys. We found that superalloys is a very good case for transfer learning. So we did two work on the transfer learning to deal with the superalloys, and they also published on the Advanced Science from 2024 and 2022. Because of time limitation, I will not uh, introduce all the details, but I would say transfer learning is a very useful way for the superalloys. So I have around 40 minutes, 50 minutes, then where I will talk about the big data and the large model. So this part, I did this from around 2023. That means that we have around, this is the work around 3 years. So why we start here? Because there is there is a famous talk from Chinese academician Wang Jian, and he said that the AI has only 7 years of history. We know that AI has a long past, but why he said AI only have 7 years of history? And as you all, maybe you know that the attention is all you need. This very famous uh, papers that has been cited more than 100, around one more than 1 billion citations, right? And with these papers, then we have these transformers. We have transformers now. We have all kinds of the large language model now, right? And also we have Alpha 3 is also based on transformers and also others. So the thing is that at that time I'm thinking about, is there any opportunity for us to choose use the most advanced AI to access in the alloy data? Because I think for the previous part is more or less the Bayesian optimization, and the Bayesian optimization is it's not new, not new. It has been used more than maybe 20 or 30 years in the industry. Uh, Although it's very efficient to deal with the small data problem for low data, but we want to involve more advanced AI. So I'm thinking about it that why how to find the big data, because you want deep learning, then you need the big data, right? But but waivers we state that we only have small experimental data set in the alloy data because it's very expensive to do experiments. Then I'm thinking about the data. If you have a very mm, how it's decide how you regard the data. If you only regard the numerical data to be data, then it has small size. But if you use a more broad definition of the data, then actually we have big data. So we said we have small data is that we said we have only small structural data, which can be easily used. But like actually we have more data that it's difficult to be used. Like the SEM pictures in the all kinds of publications, and the words, if you consider the words, tables, graphs, all these things to be the uh, data, then you did have small big data. The first thing then that you will focus on the closure field. The reason is that because here in Shanghai Jiaotong University, we did a lot of closure field. You know, AI is a tool that can be used in any things, right? So the first thing is that we use this uh, AI want to do the to involve this structured data and the unstructured data. Here, the unstructured data we use that the text. So we want to involve both the numerical data and the text data for the training. So that's the input that first we use the large language model for the text data mining, because you all know that the large language model is very powerful. This is uh, easy for them. And also we use the WAE as we did in the previous work for the data generation, and we build a bimodal uh, one partly the numerical features and the textual features for prediction, which are very important, also very important for the prediction, which involve this information processing, heat treatment, and immersion test as well. And this is the progress automatic large language extraction framework that we built uh, for the text extraction. That we use two-stage extraction and to get this framework, and it can be retrieved automatically for the equation rates and all the formula and units and all the details. We build this for the quotient problem. And then we get this big model, and then we found that the model enhanced after adding the text and can have a better performance with the more modernity. And for the analyzed that also use this X embedding methods for the semantic analyze that to prove some interpretability because before we always use this sharp methods, right? And for the words, we can use some other methods. For example, here we use that is called text embedding methods. And for the data generation, that's we use the MCMC samplings combine combine the WAE Latin space. This is almost the same as the previous work we published. And then we do the active learning. And after three iterations, we found some mechanism or laws that have very low correlation rates that can be lower than any of the previous studies. Uh, I have around 10 minutes that I want to introduce you with this our very recent work. It's called the Deep Light, which is a light alloy large language models with multi-agent design platform. Actually, this thing is very hot in China. To build all kinds of the large language model for their specific applications, not only the alloys or we call materials, but also for some like the clinical applications and also uh, uh, for some other areas like yeah. For this part, we focus on the light alloys because we did a lot of uh, things on light alloys in Shanghai Jiaotong University. I think we have the fundamentals about the 30 years of studies. Then we have many local data that we involve this the composition of the noise and also all other things, process parameters and all other things that locally we stored in our own computers. So the thing we want uh, to do is that to involve this data into these large language models and to to build data for ourselves, build for the light or noise. So that's why we call it deep light. First, that we publish, we collect almost all the light or noise publications, and then we use some methods to train this large language model. We use Q1, which is open source large language models. We also tried the Llama and the Chat DeepSeek. So generally, we use the open source large language models because we want to install locally. So because this is very recent results, so that's why we only have Chinese version. I think this year we will try to also uh, actually we don't want to this to be open to everyone. So actually Chinese is enough for us because these things is many things uh, are local things that since we only have for ourselves, we haven't decided to open it to everybody. Basically, when we do some fine tuning and or the reinforcement learning, we can for the question answer part is that if you talk with these models, it can have a better answer for light or noise. as we test with the general language model and also some material large language models, it has a better understanding. I think this is not a surprising result uh, because we involved more natural knowledge to this one. And the most important part for our model is we are doing something called performance inference or prediction, or you call it reasoning. So this is, I'm thinking about how to see this. Mm, so we know that the large language model is based on transformer and it's doing next talking prediction. So basically, it's question answer problems that you you can talk with the large language model, you can get some answers, right? And generally, the model is large language model is not good at this, or we call the mathematical calculation or some things because it's like talking prediction. If you have if you have like two like in the previous example, if you have like 700 of the data set with the composition with the properties, you can build a new network or anything regression model to do this prediction, right? So that's what we did in the previous time. In the past few days, years, there are no problems to do that. So what we are thinking that if we can give these data into the large language model, whether it can also to do property prediction. So that's a problem that we are also unsure about this because if you told me that the large language model is like talking prediction, I agree with that. You can say it cannot do that because for neural network it build a very uh, relationship, nonlinear relationship from the composition to a property, and for large language model it's not doing the mathematical things. I agree with that, but we want to try something because uh, because as we know that if a guy who study this like the light alloys for many years, actually if you give some composition to him or her, he can also have some feeling about the property of the materials. So it's hard to say that for large language model it has a broad knowledge, but maybe it's not so good at the uh, specific reasoning. And we don't know about this, but anyhow, we built around 20,000 of chain of thought reasoning data, which evolved from the alloy elements and the processing layer to the mac structure, which and the mechanism, and to the final this property layers. And this we think we extract some data, which we think has the mechanism uh, or the reasoning like humans to teach this large language model. So we test that from the if we give the composition and the processing, we want the uh, model to inference the property of this alloys. So you can see that for the general alloys, if you do nothing about that, even the ChatGPT it cannot give very good results. And for us, we can have much higher than the other models if we do the mechanical reasoning. In the previous work, we will do more about this too. And then also we built a deep light platform, agent platform, because the agent is very powerful, right? And we can do all this is data extraction. We can use some tools, and we can do to have this platform to make this uh, alloy design to be more automatic. And this is also a demo, by the way, in Chinese because we only show this in some of our customers. so it's Chinese. So we haven't translated into the English. This is how our platform work from planning to the our agent plan from planning to execution to monitoring to the reflection to and also all kinds of tool uh, use of all kinds of tools. And then all our mechanism alloys uh, during build uh, and designed with this loop from the general model to a specialized model to do learning based on this platform and then to just get the like the ultra corrosion resistant stainless magnesium alloys or the other light alloys. So we only focus on light alloys. And last, I want to show you some application of our stainless magnesium. One that we use in the novels, this notebook. Yeah. And also we have some collaborations with all kinds of the vehicles, especially the electric vehicles, even in China, because they want to also the light alloy is used to reduce the weight. So these cars also have the need to reduce the weight. So now we also have some corporations. So at last, I want to acknowledge that the center and working the center of mechanisms materials I'm now working on, and Professor Zheng Xiaoqi is the leader of our center, and also these guys are from the AI part of the Shanghai Jiaotong University. They're from computational science and all the fine tuning, reinforcement learning, and things all we all run in the computational uh, department because they have GPUs, they have techniques. It's easy for them, but we produce the data and they do the training. And also there are two guys from Xiaomi, this company that now because we are deeply cooperation, they deep like now working on in that company. It's basically it's a project that we did for the company. And also, I thank my previous supervisor, Professor Dick Hub, my work, my cover, and also my students from material science, also the food students from computational sciences. And so that's all. Thank you very much, and I'm happy to answer your questions.
Thank you, Ziyuan, for this very impressive presentation. I'm, very much surprised by how fast you can move forward to get all such, different tools integrated into such a platform. Are there questions? Okay, so then if people are getting shy, let me start. So one question from my side is that for this hardness prediction, you said that the microstructure is important, right? So then how do you get such kind of information incorporated into the Bayesian optimization?
Um, so the hardness, yes, hardness on the strength, all these things are connected with the microstructure and also the positions. So
Mm-hmm.
generally now we use the three kinds of modalities. One is that the numerical numbers that you can get, right? And this second thing is that the text, which will describe this uh, position or the microstructure in the publication or literatures. And
Mm-hmm.
the third is that we try to get some information from the pictures or the publication
Mm-hmm.
papers. And you we use the most advanced uh, tools like the uh, Gemini uh,
Mm-hmm.
from you know that that's very amazing the results. It can like they tell you uh, like the grain size also the dislocations and it can recognize the scale bars in the every picture. Actually, previous large language model cannot do that. But the
Mm-hmm.
most advanced Gemini, it can always have a so strong pause on the picture identification. It's very surprising, these results. Of course, we pay money, right? We use API, we pay, but it can be very useful. It's only around several months ago since,
Mm-hmm.
it's the development of the large language is so fast that it's
Mm-hmm.
getting more and more powerful. And they are very helpful for us to get these informations.
I see. Good. But then in this regard, so then do you think then, um, like this is a general question. Like I think a few years ago, people were talking about how to do fine tuning of the ChatGPT and so on. But now you will see, yeah, with the more advanced kind of large language models, we can directly use them. So what is
Yeah,
your vision in this regard? So then should we wait for more advanced models? How should we contribute then?
yeah, it's a very interesting question because we are also discussing about this. For
Mm-hmm.
example, in that data extraction before we use this, we use it's a Chinese large language model called Kimi.
Mm-hmm.
From at that time, 1 year ago, we think it's very useful and we think it's the best. And then we have more and more, like Claudia and ChatGPT 3.5, and then we found that the Gemini is so good for the pictures.
Mm-hmm.
So sometimes it's hard to see. Sometimes if you do some fine tuning or reinforcement learning for yourself, and then you found that the because the big companies, they are very powerful.
Mm-hmm.
Sometimes you cannot compete with these big companies, right?
Definitely not. Yeah.
Definitely not. So that's a question. So for my understanding that for the data extraction part, I think you can use this most powerful uh, large language model. But
Mm-hmm.
for the property reasoning, as I
Mm-hmm.
mentioned in the PowerPoint, I think it's not it's not the same thing.
Mm-hmm.
It's that part may maybe need more training or fine tuning of your model with your local data.
Mm-hmm. So we
So
need
it's
to
to
go ahead.
it's because the data has two parts. One is the
Mhm.
number of data, one is the quantity of data.
Yeah.
Yeah. If you have a good quantity, sometimes it can work also well.
Mm-hmm.
Mm.
Yes. Any question from the others? Okay, let me ask you another question. So then, like for such kind of agent system, so I mean, I'm wondering when you are interfacing with the hardware, so what kind of bottlenecks do you see?
I didn't mention that we involve this hardware because that's the second plan of our work. So the
Mhm.
first, the I think I plot in the PPT, but we haven't achieved that. Now
Mhm.
we are influenced with all kinds of the software, the
Mhm.
the tools, and also machine learning models. And
Yeah.
the second plan is that we are building the hardware, the experimentation.
Mhm.
Now then we can control all these things as a inner loop from the calculation to the experimentation and to the feedback and to these things. But it's very difficult for us to do now because for the alloy part that we don't have very uh, very good the we need to do many things because we cannot buy directly from the companies. This
Mhm.
automatic, like from the casting to the rolling to the processing to the things, we need to build all this equipments by ourselves. So
Mhm.
it's difficult things. So what's your question? What's your question?
My question is actually cannot you redesign the existing kind of equipment to interact with the agent?
Yeah, we are doing that. It's not a problem. It's not a technique problem.
Uh-huh. But
Mm,
then, how much? So because you need to get such kind of sensors, and also I think one of the most important elements would be robots. So then, like, then how could you modify the existing equipments to fulfill such kind of requirement?
It depends what you want to do.
Mm-hmm.
And the sensors can be a lot of problems. If you only want some data, like the experimental data, like the tensor results and the process and the temperature, this easy things that you can directly do from the pre the current. But you want to more informations, more sensors,
Mm-hmm.
then we need to design the specific equipments.
Mm-hmm.
We are also discussing. I think before I was working MPIE, now I'm working on Shanghai Jiaotong University. The most, and you said that I did much quicker than before. I
Mm-hmm.
think so. The most big advantage is that in the university, we have departments of the computational sciences, and also we have a department of the mechanics.
Mm-hmm.
We cooperate deeply with all kinds of disciplines, all kinds of other majors, and they can provide a lot of sources for us. As the problem you mentioned, I will also discuss or collaborate with the guys from mechanics,
Mm-hmm.
robots. They
Mm-hmm.
are very good at that.
Mm-hmm.
Mm, yeah.
I see.
We are doing that.
Yeah, this is amazing.
Mm.
Um, any question from audience, or it is all clear? I can stop recording if this is bit scary for you guys.